Hey there everyone, welcome to another calculus video. We're in section 2.6 from our textbook covering continuity, and for those of you in my class this fall, yes, we're skipping a couple of sections in chapter 2. We'll come back and pick them up later, but we're going to jump into section 6. And so I want to talk through what it means to be continuous as a function. We kind of have an idea of what it means to be continuous with a graph, right? I mean, if you have a graph of a function and it goes along and you can trace that graph and it doesn't ever have a hole or an asymptote or a jump or any of that kind of stuff, right? If it doesn't have one of those, if it just keeps going along and you don't have to lift your pencil or your pen, then that's a continuous function, okay? So we have an idea of what continuity means, but that's not very helpful when it comes to actually doing some mathematics with it. And so here is what continuity means. Continuity means that the limit as x approaches a of the function equals the function value at that point. All right, and that's true if that happens at any individual point. Continuity is defined at a point. And so then if it happens at all the points on your interval, then it's continuous on the whole interval. Okay, so this fact here is the definition of continuous. This is the definition, but I want you to think about this more as three separate parts. This equation up top is actually saying three things. So this is our three-part definition. And I'm breaking it down for you to make it easier for you to check whether something's continuous. The first part says f of a exists. Right? You can't say the limit equals f of a if f of a doesn't make any sense. If a is not in the domain, right, then that's a problem. The second thing is that the limit exists. The limit as x approaches a from both sides exists. So I want you to check if the function exists, if the limit exists, and then number three, this is the biggie. This is the one where the limit is the function value, okay? So you've got to have all three of these to be true, and when I write this up top, this is listed as number 3 down here. When I write this here, I can't even write this equation if number 1 and number 2 aren't true. But when we're going to try to test some functions and see whether they're continuous or not, we want to look at these possibilities, okay? And then you tell me the things that go wrong if it's not continuous. Okay, so let me show you what I mean by this. Let's take a look at an example. All right, here's a graph. I want to determine if the function is continuous at x equal -2, at x equal 0, and at x equal 3. And they do all the work for you, and you can kind of scroll down through this and read all of this work here. But I'm going to go back up to the graph and just talk you through it. Okay, so if you need to copy this down, or again, as always, I will save these video notes, and so you'll have this available. But let's take a look at -2. What happens at -2? At -2, as you approach -2 from both sides, the function goes up to +2 from the left, but down to -1 from the right. Well, what do you know at -2 then? At -2, the limit as x approaches -2 for your function, that doesn't exist. So that is a problem. The function value exists, but the limit does not. Well, as soon as the limit doesn't, you know you're not continuous. Okay? Let's take a look at x equal 3. At x equal 3, the limit does exist. The limit as x goes to 3 of f of x is what? It is 0, because it looks like we're approaching that hole from either side. However, what is f of 3? F of 3 is actually -1. And so your function's not continuous. Why? The limit exists, the function exists, but they're not the same. It's not equal to f of 3. All right, so this is part 3, right? This is trait number 3 from the 3-part definition. This was trait number 2 from the 3-part definition. Okay, and then how about at x equals 0? The limit, well, looks like you're approaching 1. The function value, there's a point there at 1, and so everything's good. So x equals 0, you're actually continuous at x equals 0. Okay, so when I give you a graph and I ask you to determine continuity, not only do I want you to decide where you're continuous and where you're not, but I want you to tell me why you're not at each point. Okay, Don't worry about these things called the terminology. Don't worry about jump continuity or any of that kind of stuff. Don't worry about that terminology. We're just talking about the three-part definition. And so when we look at that, we're looking for whether the function exists at that x value, whether the limit exists at that x value, and then if they do both exist, if they're equal to one another. So that's the three-part definition of continuity that we're going to use in our class to determine whether or not something is continuous. Okay? So that's the process. So I want you guys to check out problem number 1 here. Okay, again, do not worry about questions that say what kind of discontinuity is it. I'm not worried about that. I don't care. That you, I care. I care tremendously. But that's not something we're going to focus on. So don't worry about questions that ask about what kind of discontinuity we have. All right, don't worry about that for all these examples. Okay. All right, so let's take a look here at number 1. Is it continuous at x equal -1? Explain. Now you can look and see it's not continuous because there's a hole there, right? But I want you to explain why it's not continuous. Okay? Why is it not continuous? Well, the reason why, no, it's not continuous because the limit as x approaches -1 for f of x, can't see the negative here, so let me put it back in. The limit as x approaches -1 of f of x does not exist. That's why you don't have a limit. So that's what I mean by that. I want you to give me that information. Now it's continuous everywhere else, right? So it's continuous from -infinity to -1, and it's continuous from -1 to infinity. You should be able to lay that out, right? That's the only problem point is -1, and so we just write out everybody else. But the reason that it's not, and this is the big one, the reason that it's not is because the limit does not exist. That's different than some of the other ones, all right? So I want you to pause the video. I want you to try number 2. We're talking about this function now. Is it continuous at x equal 2? Yes or no, and explain why. Okay, explain why. Hit the pause button and try that out, and we'll come back and talk about it in just a minute. Okay, so again, clearly it's not continuous because it has a hole, but that's not what I'm looking for. The graph has a hole in it is not a calculus reason for discontinuity. It is an algebra reason, it's a graph reason, but it's not a calculus reason. And so when I come here, I need to explain why it's not continuous. No, it's not. The limit as x goes to 2 of f of x, there's a hole there, right? That's equal to 4, but f of 2 does not exist. F of 2 doesn't exist. That's why it's discontinuous there. It's not continuous there because f of 2 doesn't exist. So you do have a limit, but the function value doesn't exist. So that's what you need to see. Again, the open intervals that you're continuous on from -infinity to 2 and from 2 to infinity, you can use the union symbol or just a comma. I'm fine with that. Okay. Take a look at number 3 though. In number 3, what do we have? In number 3, we have this asymptote at x equal 3. Now, we haven't talked about asymptotes in this class. I know you've seen asymptotes in your algebra course, pre-calculus course, okay? So we talked about that. But is it continuous at x equal 3? No. Why not? Because the limit as x approaches 3 of f of x does not exist. Clearly, it doesn't exist. Now, again, we haven't talked about what it means to have an asymptote there and infinite limits. We haven't talked about that, but clearly the limit doesn't exist. It's not getting closer and closer to a point. And from one side it's going up and the other side it's going down. So clearly the limit doesn't exist. That's all you got to say. All right. F of 3 also does not exist. So there's 2 reasons, and then clearly they can't be equal to each other. If they both don't exist, they're not equal, right? That doesn't make any sense. Okay. And finally, number 4, is it continuous at 1? No. Why not? Well, the limit as x approaches 1, it's going towards this hole down here at -2. So the limit exists. And there's a point up here, so f of 1 is equal to 2. So that exists. But what's the problem? The problem is the limit as x approaches 1 of f of x is not equal to f of 1. That's the problem. That's why it's not the case. So when you want to show that something is not continuous, you have to give me one of these reasons. The function doesn't exist, the limit doesn't exist, or the limit and the function are not equal. Give me all the reasons, right? So this reason is pretty much all the time. My preference is that you focus in on the first reason, I guess, if you will, but I know my math lab requires that often you give all the problems. So if the limit doesn't exist or the function doesn't exist, then they can't be equal to each other. So a lot of times you'll have more than one reason why it's not continuous. All right. Okay, there's one more thing that I want you to see, and that is something like this, where you don't have a graph, but you need to check out what? What do I need to do? I need to check out the limit. Right, I need to check out the limit from the left and from the right, these piecewise functions, okay? And then here, I have to take a look at functions where I am going to make it continuous based on what A is equal to, okay? Or in this case, A and B are equal to. All right, so I'll do one example here for 5. Well, I'll tell you what, you guys try this one, all right? So I want you to show if this is continuous or not. So what are you going to do? You're going to take a look at the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right for this function. Okay, we did a couple of these back in chapter 2.3. I want you to try and show me what the limits are, and then determine based on that information whether or not the function is continuous or not at 3. So pause the video, finish out number 5, and we'll come back and talk about it. All right, so what happens here? As you approach 3 from the left, you're less than 3. If you're less than 3, then you use square root of x plus 1, and so we get square root of 3 plus 1, which is square root of 4, which is 2. All right, how about from the right-hand side? From the right-hand side, you're more than 3, and so I'm going to use 5 minus x, so I get 5 minus 3, which is equal to 2. All right. So I get the limit from the left is 2, the limit from the right is 2, so the limit as x goes to 3 of f of x is equal to 2, so the limit exists. What about the function value? What's the function value? If you take f of 3, well, greater than or equal to x, 3 greater than or equal to x, x less than or equal to 3, that means we plug in up top, we get the square root of 3 plus 1, which is 2, checks it out, so yes, I'm continuous at 3 because the limit exists, the limit from the left and right are the same, and the function value. So I got to see all those. I got to see you show me the limit from left and right. If the limit exists, then you got to tell me that the function value is the same. Anything that doesn't happen in that case, any of those things break down, you're not continuous. All right? So y'all try 6 and 7 on your own. And then for number 8, the same idea happens, except we have to do what? We have to look for A. So we're going to take the limit as x approaches 2 from the left of f of x, which means I'm using this one, x cubed, so I get 2 cubed, which is 8. And then I take a look at the limit as x approaches 2 from the right of f of x. If I'm bigger than 2, then I'm down here, I get ax squared. So I get a times 2 squared, which is 4a. And I need the limit to exist for continuity, so I need these equal to each other. So I need 4a equal to 8, which means a equals 2. Okay, so if I come down here for number 8, I say let a equal 2. Then f of 2 I have to check also, not because of this. This a has nothing to do with the 2 that I'm plugging in. I'm plugging in this 2 where the limit is in question. I get 2 cubed, which is 8. And so if a equals 2, f of x is continuous at x equal 2. That's a bad choice of numbers from the guy that made this problem, because this 2 here and this 2 here have nothing to do with each other, right? This is a problem in maybe understanding, but we're looking at 2 because that's where the breaking point is, and then it turns out that a has to be the constant to go in front of the x squared, okay? And that'll make it continuous. So y'all can try 8 and 9 here. 9 and 10. Actually, don't do 9. You can just try 10. Here you're going to have to do 2 of them. You're going to have to do it twice. You need to use x equal -1 and then you also need to use x equal 3 because you've got two variables to check out. All right, and of course there'll be extra problems in D2L for you to play around with too. Okay, so hopefully that helps, and we'll see you later.